All right, so now we've talked about all those factors. We can put it together and do this problem set. So I would like you to take a moment and figure these out yourself using the tools that we just gained. And so I'm assuming you've come back now from doing it. Okay, so we're going to do these one by one. So this first set, they look really similar, so what I'm going to do, if this was on an exam, I would think, okay, they look similar, let's find a point of difference. So does it have to do with the element effect? Well, let's see. The most acidic hydrogen is definitely this guy, because all the rest of the hydrogens are attached to carbons. So this is the only hydrogen that's attached to an oxygen. It happens to be the same over here. There's also definitely a resonance effect, but it's the same on both of them because it's the same carboxylic acid group. Okay, so what about the polar effect? Well, it's definitely happening. There's definitely a bromine here and also a bromine here. And they're not different atoms, but they are different in that this one has a closer proximity to the more acidic hydrogen. This one is farther away from the acidic hydrogen there. So because of that proximity, this is the more acidic molecule, because this bromine will be able to stabilize that conjugate base. Remember, we think about taking off this proton, we think about the conjugate base and how it's stabilized, and there's this big negative charge here, and this bromine can stabilize it, and that's called the polar effect. This one is farther away, so it's not going to do as much as this bromine because it's closer. So let's look at the next one. I inadvertently showed you the answer, but we're comparing sulfur and oxygen. So here we are at the periodic table. We're comparing sulfur and oxygen. So what are we comparing here? We're comparing atomic size and the bond strength. So what we're going to see here is that sulfur is larger than oxygen, so it has that bond strength is weaker, and so that makes it a more able to give away that hydrogen, which is what makes it a stronger acid. Remember, stronger acid isn't strong. I'm saying that the bond is weak, but it makes it a stronger acid because a strong acid is one that disassociates the most. So the one that disassociates the most will inevitably have weaker bonds there. So we see that, yes, sulfur does make this a more acidic hydrogen than this hydrogen. All right, so the next one, and that was due to the element effect. I hope that everybody understood that. So the next one, let's see, we have this hydrogen, it's attached to an oxygen here, it's also attached to an oxygen here, so it's not the element effect. There's a fluorine here, and there's no electronegative element anywhere on here besides the oxygen that the acidic proton is attached to, so maybe that has something to do with it. But what else is going on? Oh my gosh, there's a charge. So charge, there are two things going on here. This one has polarization happening, polarization effect, but this one has the charge effect. The charge effect trumps the polar effect, and this is, fluorine's pretty far away as well, and this charge effect is going to trump that, and that's a good thing to remember. Charge effect is a really, really big one. So, so let's look at the next one. Again, looking for a point of difference. I see that this is the same carboxylic acid, the same acidic hydrogen. However, we have two different elements. So it doesn't have to do with the element effect because the acidic hydrogen is attached to an oxygen in both scenarios. There's definitely a resonance, but they both have the same resonance, so that's not really changing anything. So now we're going to look at polarization, and there's no charge, so charge has nothing to do here, but we'll look at polarization. That's kind of the only thing we're left with. And so let's go back to the periodic table, and we can see here that fluorine is more electronegative than chlorine. So what does that mean? Well, let's go back. Since fluorine is more electronegative, it's going to be able to take more of that charge. So it's going to be able to stabilize better than would chlorine. And that's what we see. So this was, again, due to the polarization effect. This was due to the charge effect, the element effect, and again, the polarization effect. So let's talk about acid-base terminology. And we've already kind of talked about this, but here it is laid out right in front of you. So each acid has a conjugate base. And remember that and each base has a conjugate acid, so they come in pairs. And here is this reaction. So in this reaction, on one side, there'll be an acid to base, and on the other side, there'll be an acid to base. But acid on one side is going to have its conjugate base on the other side. And acid on the other side is going to have its conjugate base on this side. Okay, so can make those little pairs there. All right, so once you have identified the acids, and you know that you should be able to do that by now. You know, this is the acid because it's giving away its proton when we go to the right, and when we go to the left, this is the acid because it's giving away its proton. To this guy when we go to the left. Okay, so now we need to talk about, so where does the equilibrium lie in this reaction? And that's going to have to do with you being able to identify these weak acids and weak bases and strong acids and strong bases using the tools that we just went over. So let's talk about this one. So this is the strong acid. Why is that? Think about it for a second. Why is this acid stronger than this acid? So this acid has the charge effect, and that's a really big deal. That oxygen is really electronegative. It doesn't like to have that positive charge on it. So this is the stronger acid than this acid. So then this strong acid, its conjugate base is, you already know, you don't even have to look at this weak base and try to figure out if it's weaker than this base. The strong acid is going to have the weak base as its conjugate, and the weak acid is going to have the strong base as its conjugate. So now that we've figured that out, we can tell ourselves where the equilibrium is going to lie. So is it going to lie with the reactants, or is it going to lie with the products? Well, our strong acid is over here in the products, and we know that a strong acid is going to disassociate, and it has that large Ka value. So in this case, the reaction is going to go right to left, and we're going to be over here. And over here, a weak acid is more stable. It's not going to disassociate as much, and a weak base isn't going to be as reactive. So this is where the reaction will lie primarily, and you can use your knowledge of weak acid and weak base, strong acid and strong base to figure that out. So when thinking about the bases and how strong they are, so we are comparing this base to this base. So what makes a base strong? Well, its ability to pick off a proton. So again, the charge effect comes into play. This is charged and this is not. The charged species is going to be more unstable. Charge is always more unstable, but this species is going to be more unstable than this species. So it's going to pick up a proton faster and be more reactive than this species. So that's just more evidence for the case that we made that this will be where the reaction lies primarily. So what's happening in an aqueous acidic solution? An acid is added to water, and equilibrium is established by the system. So we just talked about that, right? We add water to something, and then it establishes its equilibrium depending on the strength of the acid. And so why does it reach that equilibrium? Well, it's going to go to the more stable side, and that's because it's lowering the energy of the system that has been created. The acidity of the system depends on the relative stability of the products and the reactants. It depends on whether the products or the reactants are more stable. So that's, yeah, we just talked about that. So a higher energy product and reactant will react more, and so they will react until there's more of the more stable pair. So we can also think about which base can hold on to the proton better, water or the conjugate base of that acid. So water, remember what happens. So you have to think about like what happens when water acts as a base and picks up a proton. Well, it becomes H3O plus. If something more negatively charged, like in the example that we just had, and we can go back to that. So this is when it picks up its proton, it becomes this, and it's going to hold on to that proton more, and because it's a weaker acid, more than this species, once it's been protonated, coming from this base, is going to hold on to that proton because it's as a stronger acid, it's going to disassociate, it's going to react. So that answers that question, and the next question, how much better? This is the question of equilibrium. So we just talked about that. The better a base can react and pick up a proton, that's going to imply where the equilibrium is going to lie. Instead of using K equilibrium, we're using Ka to measure acid equilibria. So we've talked about that all throughout this lecture, pretty much. So if the stronger acid is on the reactants side, then it's going to favor the products. So here is a general description of what's going on. So remember, A is atom. And so this, remember from general chemistry how we did this. It's products over reactants, but we ignore water because it's a liquid and it's essentially constant. So we're just looking at products over reactants over here. And we are going to look at the Ka. So we'll look at the Ka of this guy and the Ka of this guy. So since each acid has a different Ka, that's its acid, it's the dissociation acid constant. So if this was a crazy high acid, and this had a Ka that was a little bit lower, then that means it would favor this side. But if the opposite was true, this, because it has that charge, I mean, it's most likely going to be a higher acid than this guy, depending on what A is. But if that's true, then it will go this way. So again, this is the measurement of a strength of an acid. The hypothetical situation, HA is this crazy strong acid, stronger than H2O. And we kind of talked about that, so I'm going to skip that. Okay, so this is your general little points to talk about. It is more convenient to express the dissociation constant in terms of pKa, and that's what we're going to do. We're not really going to talk about Ka, but just know what Ka is and what it means. Don't forget it. The lower the value of the pKa, the stronger the acid. The higher the value of the pKa, the weaker the acid. The higher the pKa, the stronger the base. You have to keep all that straight. For bases, you can look at the pKa of the conjugate acid. A strong base has a high pKa for its conjugate acid. So it's kind of, you're gonna have to like talk yourself through these a lot and get used to the terminology, and it'll help. So. A little fun. It's like a tug of war between water and the anion for the proton. Who's going to pick up the proton? All right. So that is the end of the lecture. So thanks for sticking with me. And this is just a couple extra websites for you that you can check out. Could be helpful. And that is my email address. I will be available by email pretty much always, and I'll try to get back to you within 24 hours. And if you would like some help after class or something, email me and I can make some time. And I'm also going to be posting videos, and I'll let you guys know when I post them. But I'll be posting these videos on skills throughout the semester to help you guys out. So, all right, let's have fun this semester.